طيب بسم الله الرحمن الرحيم. We started to talk about transport layer services or transport layer security. As we said, TLS was originally standardized to provide secure communication between a web client and a web server. Later on, of course, it was widespread to be used in different other services other than the web services, like email clients and other types of services. TLS, at least version 1, was designed to deprecate and to replace SSL, which was used originally for securing HTTP. But TLS version 1, because it did not have backward compatibility, it was not actually efficient in replacing completely SSL. And that's why TLS version 1.1 and later versions, they have supported backward compatibility to try to gracefully deprecate SSL. As we also said, transport layer security can be integrated as part of the operating system, which means that applications can seamlessly set some flags to support TLS, or it can be actually integrated into the application package, like a web server. So Google Chrome, for example, has its own component of TLS. Or if it's built as part of the operating system, then your Microsoft Outlook can utilize TLS service, which is integrated already in the operating system. So today we will start to talk about the layer stack of TLS. So as we have said before, TLS works on top of TCP. So it kind of inherits all the features of TCP, being like connection oriented, provides bidirectional communication, order delivery. All of this is already inherited and leveraged by TLS. So the layer stack here shows like HTTP. HTTP in the 7-layer stack, the 7-layer stack, not the 4-layer stack, in the reference model, 7-layer stack. HTTP lies exactly in which layer? Not in the 7-layer stack. In the 4-layer stack, yes, it's because there's TCP/IP stack, which has only 4 layers, right? Physical layer, data link layer, network layer, and transport layer, and application layer. طبعا physical layer and data link layer is network access layer. So there's only 4-layer stack. Okay, but the 7-layer stack, included in the reference model, defines 7 layers, including session, presentation, application, and all of this. So in the 7-layer stack, HTTP accurately lies in which layer? No. HTML is the presentation layer. HTML is the presentation layer. HTTP lies in the session layer. Okay? What is the meaning of a session? What is the meaning of a session, Aslan? Okay? Session provides accumulation of conversation throughout the communication. Connection does not necessarily provide that. So when you connect to a web server, for example, like you want to buy something from Amazon, okay? So you have to click and you have to do some workflow, right? Throughout this workflow, you kind of accumulate information as you go through the process. So for example, you add some items to the shopping cart, then you move to the next level, so the shopping cart is still there. So the accumulation of information from one step to another, this is actually maintained in what we call a session context. HTTP provides that, okay? And that's why in HTTP there is a session flag called a resumable. If you know that flag, resumable means that this session, okay, will continue to be valid as we go through the process. If this resumable is 0, this means that all the session context, all the accumulation of information is gone. That's a very important concept, okay? So when we say resumable is 0, this means that the session is done, which means that everything in the shopping cart, all the credit card information, everything is gone, right? So all the accumulation of information is gone. It's like when when we have any conversation between human beings, right? So we send each other like some messages. Our brain actually absorbs that, accumulates information. So when we leave each other, maybe the session context is gone, okay? But as we go through the conversation, we exchange ideas, we accumulate some information through the conversation. So that's the function of HTTP. So I like to always visualize that. So if we talk about a client and a server, or as we always say, Alice and Bob, right? So the HTTP provides some kind of session level information which accumulates information as we go through the conversation, or we click on certain links and we go through the next step and so on and so forth. HTTP maintains that session accumulated information. We're not talking about security yet, right? HTTP underneath uses what? TCP, right? So HTTP may in fact establish one or more TCP connection. One or more. In many cases, these TCP connections are short-lived connections. Sometimes when you click on a link, okay, you establish a TCP connection, you exchange certain information, and then the connection is gone, right? But the session information is accumulated in the session context, here, not here. Okay? So HTTP in general maintains some one or more short-lived TCP connections. Okay, this is very important. Okay, so that's the situation. That's the overall picture without security in this picture. Okay, so TLS comes to this picture in two levels. As we can see here, we have some protocols in the session level together with HTTP. Okay, so here TLS has what we call TLS session. In this TLS session runs all these four protocols, and we'll talk about the functionality of each one. Okay, so there is the TLS session, which maintains what we call, or what we will call in a minute, the cipher spec. The cipher spec is the specification for all the security algorithms and mechanisms that we need to use as part of this session. Okay? So the TLS session then will use the cipher spec to create what we call a connection state. The connection state is used to provide a tunneling service on top of TCP to encrypt everything and to maintain all the message authentication and so on and so forth. Okay, so these are the two levels. So this tunnel is what we call a record protocol. So the record protocol provides that tunneling service on top of TCP to have a tunnel to encrypt everything on top of the TCP connection. Okay, and this connection state is instantiated from the session state. The session state maintains what we call the cipher spec, which provides all the mechanisms for security within that session. And of course, the reason for that naturally is that, as we said before, is that not in every connection we need to establish a security context, right? So the security context is in fact maintained in the session level. And from that security context, which is what we call session state, we can instantiate multiple connection states. Okay? So when we create a new connection, a new TCP connection, we create one connection state from the session state, right? Using the cipher spec, and then we use that for that particular connection. واضح كده? So this is the overall picture. So now, what are these protocols? As we said, the record protocol is easy. This is the one that provides all the encryption and message authentication in a nutshell, the tunneling service on top of TCP to secure the communication within that tunnel. Okay? The handshake protocol is the one which is responsible for, this is the main one, which is responsible for user authentication and key exchange. Similar to IKE or similar to all the other security services that we talked about before. The change cipher spec is a very, very primitive protocol. It's not just a protocol, it's just one single message that says that, we instantiated a cipher spec, so now we can use this cipher spec for this particular connection or connections. For the upcoming connections, we are going to use that particular cipher spec. So change cipher spec meaning that we have now created a new cipher spec based on user authentication and key exchange. So we'll talk about the details of this. And based on that, we need to use that cipher spec for all the upcoming connections. Okay? Which means that this cipher spec is to be used to instantiate all the connection states for all the upcoming connections. Okay? There are certain conditions based on which we need to renew the security context, or in other words, the cipher spec. One of them is that there is some alert protocol that, again, we discover some weird behavior, and based on that, the alert protocol may in fact be used by the client or by the server to report some warnings or some errors, like some suspicion for a replay attack or some suspicion for any kind of breaching to the communication. So if that's the case, depending on the type of alert, we'll talk about this, this may actually instantiate another handshake protocol to renew the security context by actually going through the user authentication and key exchange one more time to renew the security context, and then we go to the change cipher spec to use that particular cipher spec for all the upcoming connections and so on. So one alert may in fact trigger the handshake, which consequently cause the change cipher spec to use that particular cipher spec for all the upcoming connections. Okay? Type. What is the heartbeat protocol? The heartbeat protocol, we used heartbeat before, صح? In several contexts. Anyone remembers heartbeat is used for what? Right. We used it, for example, in dynamic routing protocols to exchange some hello messages or some heartbeat messages between the routers, so that every router would know whether the next hop is actually alive or not. So to keep the connection between the two routers, valid or alive, right? But this is used between a client and server. This is end-to-end communication. So what happens is that a scenario that you go through the shopping cart and you add all the shopping cart, and then you enter your credit card information, and now you need to click submit to buy everything. And now an idea comes to your brain, you need to think twice, So you leave the session idle. And you start thinking whether you should click on submit or not. So you may actually think for a minute, for two, for three. What might happen then is that from a security perspective, the firewall may in fact invalidate the session. The firewall, okay? So even if the client and the server, they still maintain the session and they think that the session is still alive, the firewall in the middle may in fact prematurely invalidate that session and block all the upcoming messages going between the client and the server.
Because there is no traffic for a while?
Because there is no traffic for a while. So that's why sometimes when you leave a web page open for a while, and then you click, it says your session expired, right? Of course, there is always a limit, but we need the client and the server, they need to maintain certain control on that limit, okay? That's when this heartbeat protocol becomes handy, because this means that even if the tunnel has no messages to be sent, the client and the server use that heartbeat protocol to send some messages to report to the firewall and all the intermediate servers that this session is still alive, even if the user is still thinking about buying or not. Okay? So, but again, I mean, these messages, after a certain period of time, it will stop, in which case the session will expire. So the heartbeat protocol is used to maintain the session state valid, okay, even if there is no user interactivity on that session. واضح كده? So this is the overall picture. That's what we need to talk about in the remaining part of the lecture. So, of course, naturally, as we said, TLS maintains what we call TLS session. In the TLS session, we instantiate the cipher spec. The cipher spec corresponds to the session association of IPsec. That's exactly it corresponds to each other, right? But here we'll see some differences, some fundamental differences, of course. Again, based on the fact that TLS works on top of TCP, بينما IPsec works on top of IP. Okay, so that has certain implications. We'll talk about this. So the TLS session is an association between the client and server, which maintains the security context. The security context is defined first and foremost by the cipher spec, which defines all the set of algorithms and mechanisms which are used for user authentication, for key exchange, for confidentiality, integrity, all of this, right? So naturally, of course, this TLS session maintains multiple connections. So it's one-to-many. Okay? So the TLS session with the TLS connection is actually one-to-many. Again, similar to the feature of TCP and HTTP. HTTP instantiates multiple short-lived TCP connections. So that's exactly the same. ماشي كده؟ So طبعا TLS session is used to avoid expensive negotiation of new security parameters. So we're not going to perform user authentication and key exchange for every single message because this is very expensive. So the idea that we have used since the beginning of that course is that we always maintain some security context, and then from the security context we maintain what we call the master key. And this master key is to be used to instantiate multiple اللي احنا بنسميهم transient keys, and these transient keys is to be used for a certain period of time. So for this particular case, the transient keys will be used for the TLS connections, right? The TLS connection is a transport layer thing that provides suitable type service, layer tunneling service. For TLS, such connections are peer-to-peer relationship, which means that it provides bi-directional communication. And as we will see in a minute, the TLS connection maintains 3 keys from the client to the server and 3 keys from the server to the client. Okay? And every connection is restricted to one session, so there's no possibility that you can have many-to-many. I have to say that these TLS connections can work sequentially or in parallel, which means that so if we talk from a time perspective, we have the client and server, and throughout the time, we maintain like certain session level conversation. So this is a time. This is the time domain. Right? So this is the session level conversation, which maintains information as we go throughout the interaction, right? So this is the TLS. This is the TLS session. Okay. Within that session, that we may have some short-lived connections or TLS connections. And these connections, by the way, they may happen to be parallel or sequential, depending on the interaction between the client and the server. Sometimes like when you click on a link, that causes a download of 100 files. Okay, HTTP in that case uses separate TCP connection for each file, which means separate TLS connection for each file. All these connection states are again instantiated from the same cipher spec. واضح كده؟ So these connections might be instantiated in parallel or sequential depending on the interaction between the client and server.
And all this is going on the 443 port?
Right, of course. Yeah, yes, of course.
But they are at the same time with many connections?
Yes, yes, of course. All of them are in the same port. On the same port اللي هو طبعا خد بالك same port from the server side اللي هو 443. But the source port is different, definitely. Source port is different. واضح واضحة دي.
Something above 5,000.
Yes, exactly. 4,000. Okay. So the socket connection is defined by all the four values اللي هو source IP, destination IP, source port, destination port. All of these four numbers, they identify the socket connection. Okay. So any change of these numbers, it means it's a different socket, right? واضح كده? So that's in the time horizon, yeah, in the time domain. Any other questions? واضحة كده؟ ماشي. طيب. So now we're going to talk about the session state, which corresponds to the اللي هو session association in IPsec. So the session state is defined by, first is اللي هو session identifier, similar to SPI, security parameter index. And I'm trying to relate things so that it helps us to, يعني not to confuse you, but it helps us to understand, because it's these standards, they use similar approaches more or less, but again the differences come because of the inherent features of the protocol underneath. So now, for example, we'll see some differences and we'll try to identify why this is happening. So session identifier is used to طبعا هنا ما فيش اصلا بقى security policy database صح؟ و security association database. Why? Why?
That one, because that was built on IP, but this is an application level where you have
Right. So what is type? Why? But why on IP is different from TCP? Remember the overall picture again. If we go from network access control, security, we provide security for a physical connection between the station and the access point. Okay, it's agnostic to the type of traffic. Security between physical devices, which is again based on the fact that network access control provides point-to-point communication between physical devices. The security is the same, but this is agnostic to whatever application traffic processes running on that host. We don't distinguish between all of these applications and traffics. واضح? When we tried to talk about IPsec, we said that it's a host to network or network to network, in which case we need to worry about the type of traffic, and we provide different behavior for each type of traffic. صح؟ ماشي؟ But still we provide security between host to network or network to network. Again, this aligns with the service of IP, which provides host to network or network to network communication. ماشي؟ But here we need to distinguish different behaviors for different types of traffic. ماشي؟ Here بقى هو one traffic أصلا. Why do we need to have a database أصلا? It's one traffic. هو أصلا client and server. It's one traffic. It's just the fact that the multiple connection doesn't mean that it's different traffic. It's one traffic. A traffic is defined to have a communication between two application endpoints. صح? So it's the same traffic. Why do we need to have a database and different behavior? Different behavior for what? It's the same traffic, same service. ماشي؟ We don't need any security policy database. We don't need to provide different behaviors for different traffic. It's actually one traffic. ماشي؟
TLS is not only for web, right?
Right. صح، بس هو it's used for one service at a time. يعني هو IPsec can provide security for all these services
Yes.
combined.
Yes.
صح? So we need to provide different behaviors for different services. But here it's only one service.
You have to choose like this application, and you have to actually
Exactly. So a
manage
TLS is to
yes.
provide security for one particular application, not multiple applications at the same time or يعني combined or concurrently. واضحة كده؟ So we're trying to relate things to each other يعني we're trying to give you يعني طيب the peer certificate is used for authentication. The peer certificate which is maintained at the client session state, okay, would have the public key for the server basically, and the other way around. So on the server side, the peer certificate would maintain the public key for the client. So this is to be used for peer authentication, peer user authentication, not message authentication. For message authentication, we can use بقى HMAC والحاجات دي. ماشي؟ Compression method. We didn't talk about compression method before. Why do we need to have compression here? ايه compression؟ جالنا جديد ده ما ايه؟
For the data that's
Okay. Why do we need to have compression? What is the relationship between compression and security? ليه اللخبطة دي يعني؟ أنا عارف بضغط عليك العشر الأواخر بقى وليلة وترية وبتاع. طبعا الموضوع مش في المود خالص يعني، بس معلش خلينا نحاول. تاني برافو عليك. Yes. So compression would help reduce the overhead of encryption complexity, right? So if you have a large message, of course, the time that you would take to encrypt that message would be, again, proportional to the size of the message. So if you reduce the size of the message, you reduce the overhead of encryption. Because encryption is expensive. But what type of compression are we talking about here? Lossless compression, of course. We cannot. طبعا هنا you know that compression can be in two forms: lossless compression or lossy compression. Lossy compression, you may actually afford losing some information from the original information. Use a little bit of information with the hope of trying to reduce the size even more, right? But here we're talking about lossless information, definitely. And actually, compression here is optional. Compression is optional. It's defined in the standard as optional. You may actually not perform any compression and do the encryption directly for the entire message. ماشي?
Why is it an option here but it was not before?
Why is optional what?
It's an option here but it was not before in other.
Compression did not exist in other standards أصلا. اللي هو قصدك يعني مثلا for IPsec مثلا في الحاجات دي، هو الستاندرد did not mention anything about compression. يعني there may be a reason for this and there may not be a reason, I don't know. Maybe here because you are providing مثلا end-to-end communication between a client and the server, whereas for the other one you have مثلا security for different types of traffic. So if you define compression, you will have to again define different types of compression for different types of traffic, and that will complicate the communication, so they decided not to have it. But here again, it's optional. يعني it's not mandatory. It's not something mandatory. It's mentioned some implementation of TLS, they may choose not to have compression. خلاص. I'm not providing any compression feature because it's optional in the standard. So if you do that, you still comply with the standard because the standard says it's optional. The cipher spec بقى is the main, يعني is the core information which maintains all the specs for all the security mechanisms, including بقى user authentication. Are we going to use certificate? Are we going to use مثلا user ID and password? Of course, all these mechanisms, they have certain codes, and these codes will be stored in the cipher spec. In the standard طبعا they have a lookup table of all the algorithms and some codes related to them, so it's maintained within the cipher spec. Okay, so you have for key exchange, for user authentication, for encryption, for MAC, for initial vectors, ماشي. All of these. And the master secret key, of course, this is the most important thing. From the master secret key, we can instantiate multiple keys using a pseudo-random function, ماشي, and we'll see the process of this. And is resumable, which corresponds again to the resumable flag in the HTTP session as well. This is similar. So the security session is to be invalidated using that flag. So if that flag is 1, this means that the security context will remain. But if مثلا you get an alert, or after a certain period of time, or after disconnection, or, then this flag might be set to 0, which means that all the security context will have to be dismantled completely. ماشي?
Isn't this heartbeat?
لا. No. No. Heartbeat is used to help decide whether the session will remain or not. But this session state maintains that flag to say whether that session is in fact valid or not. Okay? The heartbeat may in fact check that flag before sending the heartbeat.
Okay. If it's false, it will stop.
Yes, if it falls, it will stop sending the heartbeat, which means that, okay, the firewall may now decide to invalidate the session and make it invalid. ماشي? طيب, as we said, the session state can be used to instantiate multiple connection states. صح? So this is about the connection state. And again, the master key is used to create all these transient keys. ماشي? All these transient keys. So the connection state maintains set of keys. أول حاجة, there is the server and client random sequence. ده جديد ده. يعني we did not talk about this before in IPsec. يعني here TLS maintains a unique approach for exchanging some random. It's similar to nonce. يعني you can think of it as nonce. يعني ماشي? But we'll see why this nonce or random sequence is actually used. Server write MAC secret, اللي هو server write, which means that when we say this is the client and this is the server, okay? So server write, this means that this is the server write key. So the server uses that. So there is MAC and there is اللي هو server write key. Server write key is used for confidentiality or encryption. And there is also initialization vector. Okay? So here, the client will have to do the same. Uses server MAC and encryption and IV. So just the fact, remember, just the fact that it's a bidirectional communication, it doesn't mean that we use the same keys to encrypt the traffic going back and forth. So we have to use a separate set of keys for each direction. Okay? So we'll see back, man, when we talk about the disconnection, we'll see there is a reason for this. طيب, so here we talk about the random sequence, and we'll talk about why we need that random sequence. So this is the type. Here we have a sequence number. Sequence number is used for what? The multi-TCP fee sequence number. My sequence number here is used for what? Huh? For replay attack, صح? طيب, هنا we don't have a window. صح? In IPsec we talked about a window. Here we don't have a window. Why? Why we had a window for IPsec? And here we don't have a window.
Because the packages might change there.
Packages might change, eh?
I mean, because this.
أيوة.
They might not arrive.
For which case? For IPsec. But here they arrive in order, صح? So again, TLS works on top of TCP. So TCP ما بيهرجش في الأوردر. TCP يعني order. TCP order delivery مع order delivery. ممكن يقعد سنة بس يعني order delivery reliable, 100% reliable. So So it's enough to use one sequence number, okay, to mitigate replay attack. We don't need to have a window. We don't have unreliable traffic. خالص. ماشي. Here, traffic is reliable, connection oriented, and ordered. So sequence number is enough. واضح كده؟ So this is the session state and the state. Type, there's nothing here. There is the record protocol. Record protocol is one of the protocols that we talked about in the session level for TLS. It provides طبعا confidentiality and message integrity. So both of them are instantiated from the handshake protocol. The handshake protocol is used to provide a user authentication and key exchange, based on which we can instantiate the connection keys, اللي هي server write key و client write key for Mac and for encryption and so on, which are to be used to provide confidentiality and integrity. So there's nothing actually new in this slide. يعني. طب here بقى this is the protocol level for the record protocol. Okay, so these are the steps in the record protocol. So we have طبعا the application data is coming from the web application or from email application or from whatever. And as we said, the first thing we do in the transport layer is to divide the application traffic into we call it segments. I like to call it segments. So this actually synchronizes with the terminology that we use in Network 1. So this is the right terminology. So the protocol data unit in the transport layer is called segment, not fragment. Fragment is used for IP, صح? We use it for fragmentation, IP fragmentation. So not to confuse, this is actually segment, not fragment. So the application level traffic will be divided into segments. So these segments will need to be transmitted over the TCP connection. But before that, of course, we have TLS. So TLS works on top of TCP. So before sending it on the TCP socket, we have to do the security part. So the first part is to optionally provide some compression. And compression is done before encryption, again, to reduce the overhead of encryption. So when we do this, we reduce the size of the message, and then we do the encryption, and we add the MAC. So we did that before several times, so there's no issue. So here, we add the MAC first, and then we do the encryption. In IPsec, we did the other way around, right? So there's no significant difference between doing one before the other. And then we append the TLS record protocol header. This TLS header, we'll see in a minute, it actually provides the type of the message. Because here, this message might be a data message, or it might be one of the protocols that we talked about, اللي هو heartbeat protocol, alert protocol, or something like that. So in the TLS header, we maintain the type of this message. Okay, so these are the steps for. Yes, هو in both sides it reports the fact that you encrypt the whole thing, and then TLS header gets appended, which means that TLS header before sending this over the TCP connection. So this is in fact the TLS header. So this is the TLS header. Here we have the content type. The content type is one of the 4 types we talked about before, whether it's a data message, alert protocol, or change cipher spec, and so on. We'll talk about these 4 types. Major version and minor version. These are the versions for TLS. So in IPsec, we used to use a 1, 2. That's why there's only one version type. But here, they usually use TLS goes by 1.0 or 1.2 or 1.3. I think now we have 1.3, TLS 1.3. So if it's 1.3, the major version will be 1, and the minor version will be 3, something like that. Not anything specific. Type, compressed length. Why we say compressed length? Compression is optional, right? But this compressed length is actually provides the length for up to here. ماشي. What is this part بقى؟ اللي هو إيه؟ لا, this is MAC. This is MAC. Right? اللي هو ايه؟ الايه؟ link. Length. Yes, ما هو this length reports this, the length to here. So what I'm saying, طبعا we have, by the way, TCP header itself maintains برضه the ايه? The payload length. So we know the length, right? But there is like a difference between the length for this and this particular part and the MAC. The MAC, we know the MAC. خلاص. ماشي? But the compressed length is the length up to here. So there is a small part here which is used for a for a أيوة padding. أيوة برافو عليك. Yes. It's for random padding. نفس اللي احنا عملناه برضه في الIP كان كده برضه. Okay. So random padding again is used to mitigate the traffic analysis. That's why we need to report the compressed length, because otherwise actually the segment length and everything is reported as part of TCP header, right? But here we need to report the compressed length without the padding. ماشي كده. And then this whole part will be طبعا when we say TLS works on top of TCP, this means that the payload is encrypted by the but the TCP header is not encrypted. متفقين دي عليها طبعا. This goes without saying. ماشي؟
Padding, right? So I thought like it's kind of no one will know this information, but it's not encrypted. So what's the point of having a padding? So it's like to hide this information from somebody when it's not really encrypted.
Right. Oh, the TLS header has to be exposed, I think, right?
Yeah, because this one is not encrypted, but
It says that the encryption is this part.
mm-hmm.
So what I'm questioning here, the TLS itself is not to be encrypted, صح? The TLS is not to be encrypted, صح? That's a good point. The compressed length reports the length without the padding.
Yeah.
Okay, that's a good question. Yeah, I will have to check that. صحيح. But I know this is in the standard. This is what happens. The compressed length is the length of the payload without the padding.
Because we're trying.
Because otherwise يعني هو the segment length is already reported in TCP.
And even like some information like the minor and the major version, I think this can be encrypted. Why would it be encrypted? Like when the other part, when you decrypt, you will know which version or which, even the maybe some data.
Are we talking about the fact that TLS header is يعني the content type is it needs to be read before you do the decryption, which means that the TLS header itself
Maybe because it
may be encrypted.
The compression algorithm
Is not to be encrypted itself, which makes sense. But if you have the compressed length without the padding, you are right. This will report some information that the length already. Yeah, we'll have to check that. Yes, I'll have to check that in the stand.
I have like a question. So the compressed length is in the header and it's not encrypted. So
Right.
it's like anybody can know what's part is padding, what's part is not. It's not really like a secret.
هو ده
Like we have the compressed length,
right.
so we will know which part is.
So these are the 4 types for the content type. So the content type may be like a change cipher spec, in which case the message payload itself may have only one flag to say, use that particular cipher spec for all the upcoming connections. That's it. Like this cipher spec is now active and you can use it for all the upcoming connections. So it can be as simple as sending one flag to say change cipher spec. That's it. So you may in fact perform handshake and create or instantiate another cipher spec. Once you send this message, this means that, okay, so for all the upcoming connections, you need to use that particular cipher spec. Or it can be an alert protocol. We'll talk about the alert protocol. If the message content refers to the alert protocol, then the message payload would have those two fields, 1 byte each. This will report the level, and this will report the type of alert. The level, we'll talk about this. The level is either warning or fatal mistake, and the alert is actually a code that reports a particular alert. ماشي? C reports the handshake messages, which will go back and forth between the client and the server. We'll talk about this in the next slide. This بقى reports يعني هو ده طبعا this is the major part where we have to perform handshaking between the client and server. This is the most complicated part. Or the record protocol data content بقى اللي هو this part is encrypted and it reports the message content will be in that case will report like some data, actual data that is being communicated between the client and the server. ماشي؟ طيب, so change cipher-spec protocol, it's very simple. It consists of a single message. So single message which consists of a single byte with the value of 1 to indicate that you can use this cipher-spec for all the upcoming connections. That's simple. Alert protocol here reports TLS related alerts, which might be that there is some weird behavior and I'm seeing some مثلا truncation attack, or I'm seeing some type of replay attack, or there seems to be something going on, things like that. So these messages could be either warning, which means that I'm reporting a warning, but you can still continue communication. There's nothing to worry about. I'm reporting some warning, but you can continue the communication. Or fatal, which means that immediately you have to disconnect, or you have to make this connection invalid. So when you make a connection invalid, this doesn't necessarily mean that the session is invalid, right? So other connections on the same session may continue. Why? Because connections, they still use different connection states. ماشي? So if a connection is to be invalidated, that doesn't necessarily mean the session is invalidated, right? واضح كده؟ ماشي. So the second byte contains the type of alert, which is the detailed error that happened. The detailed error that happened. And usually طبعا in the standard they have very, very long list of lookup table that reports all the possibilities for all the messages, and there is a code that gets assigned to each of these messages. واضح? So the handshake protocol allows the server and the client to authenticate each other. This is the most important part, and that's what we need to talk about. The handshake protocol is used before any application data is to be transmitted over the connection tunnel. So that's what we need to talk about. So these are the messages that the client and the server, they exchange to provide handshake. So there is client hello, server hello, certificate, things like that. We'll talk about this in the next slide here. So that's the sequence of the messages as part of the handshake protocol. So again, we try to relate things with the IPsec, but again, there are some differences, sometimes significant differences. So here, again, the context is that we're trying to provide handshake or user authentication and key exchange between a client and the server end-to-end. One traffic, one application, two application endpoints, between two application endpoints. So here, so again, similar to what we have done before, these are divided into 4 phases, except that the 4th phase, as you can see, it does not belong to the handshake actually, because it has the change cipher-spec. So the change cipher-spec is actually a separate protocol. So once you actually finish all the handshake, then what you need to do is that the client will say, okay, so it informs the server, change cipher-spec, I'm going to use the cipher-spec that we have both agreed on, I'm going to use that for all the upcoming connections. And the server will do the same, and that's it. So that part is easy. So this is phase 4. 3 phases, these are defined as follows. So the first phase, the client and the server, they exchange capabilities. They exchange capabilities for all the TLS version, what is the maximum TLS version, and so on. In the second phase, the server performs its own part of the authentication to the client. The third phase, the client will do the same with the server. So phase 2, server will authenticate itself to the client. Phase 3, client will authenticate itself to the server. And then at the end here we have a master key. Once we do that, we have a master key. ماشي? So we have a master key. From that, we can instantiate all the transient keys, the server write key, the server MAC secret, all of these. Okay? And then we can say, use that cipher spec, and that's it. So going deeply back into each phase. So, of course, naturally, as we always say, network 1, in client-server communication, the client is always the initiator for the communication. ماشي؟ ده تعريف الكلاينت أصلا. مفيش سيرفر بيبعت لي حاجة من غير ما أطلبها يعني. I have to request something from the server so the server can give it to me. So the client is always the initiator for the communication. So similar to the connection establishment, which first goes from at the TCP level, which also goes from the client to the server. Also for TLS, the client would initiate the communication by sending its capabilities to the server. Capabilities include what? Include what is مثلا the maximum TLS version that I have or that I can support. Sometimes the client مثلا can support version 1.3, but the server does not know 1.3. The server only has 1.2. So in that case, they have to use 1.2. ماشي? Also, the client can exchange information about all the capabilities when it comes to user authentication. I can actually provide authentication using certificates or using user ID and password, using different methods. ماشي? All these methods, they have codes in the standard. And in this message, I send these codes to report to the server that these are the capabilities that I have. Which of these would you like to use? And that's what happened to us. Sometimes when we click مثلا on a link to connect to a server, sometimes we get a message. I'm not sure if some of you have encountered that. We get a message saying that, would you like to exchange the certificate with the server? Or sometimes you get a pop-up window saying you have to enter user ID and password. Okay, so this is part of negotiating these capabilities. The client first would say, I have these capabilities, and the server would say, no, I want you to use this. Okay, so the client would send its capabilities to the server. What type of mechanism you can use for user authentication, for key exchange? For example, for key exchange, I can use Diffie-Hellman or I can use RSA. For encryption, I can use AES, I can use triple DES, I can use whatever. So all of these are reported in terms of codes. And then the server would report back saying, okay, we can agree to use TLS 1.2, we can agree to use certificates for user authentication, we can agree to use this. Okay? So these are just to report and to exchange capabilities only. طيب. So just the fact that the client is the initiator of the communication, it doesn't mean that the client is the one that also drives the authentication process. Okay? So the client requests, but the server is the main driver for the authentication. So the server will have to drive the authentication part by, first, server sends the certificate to the client to authenticate itself to the client, and the client verifies that certificate, of course, through the certificate authority and so on and so forth. And then we know that, okay, this server is authentic. So that's the first part. Server key exchange, this message is very important. Server key exchange, this is the message where the server usually reports all the parameters related to the key exchange. We talked about that before. So if it's, for example, Diffie-Hellman, what do we report? فاكرين اللي هم الايه؟ لا, if it's RSA, we report the public key.
The master key.
لا, for مثلا Diffie-Hellman, we use ايه؟ Alpha, Q, Y, صح? We report all these values, صح? and هنا بقى طبعا في برضه حاجه برضه very specific here. The server would also send some signature. This is a new approach which is used as part of TLS. So here we use طبعا هنا to send some public parameters for key exchange. And also this is one. Two, we report a signature. This signature بقى طبعا احنا we report in the certificate, we reported already the public key. For the server sends the public key to the client, and the client use that certificate to verify or to authenticate the server. So now the client would have the public key for the server, which is maintained as part of the peer certificate in the session state. ماشي? In the server key exchange, the server sends a signature which is a hash value of all the messages sent before that by the server. So all the hello, all the server hello, all the certificate, everything. It creates some hash based on all these messages and send it as part of the server key exchange. Why? Because the server will hash this value and encrypt it using its own private key, which can be decrypted by the client, so that the client verify that the one who sent all these messages is in fact the server, and there is no truncation attack or there is no impersonation attack that happened in the middle of this. This is why this is done in this particular case, is because here we provide end-to-end communication, and one of the common attacks for client-server applications is the truncation attacks, is that one can come in the middle and actually block certain message from going to the server or from the server to the client. Any truncation attack would make all this communication invalid, and this signature is used for that, is to make sure that طبعا truncation attack is followed by impersonation attack. So I'm going to block this message and send a message from my side giving you certain parameters that will allow me to break the communication. Okay? So in order for the client to make sure that the server is the one who sent all these messages, here as part of the server key exchange, we send also a signature, which is the hash value encrypted by the private key of the server. Okay? By the server, but مش the certificate authority, by the server, to make sure that the server is the one who sent all these messages and no one else. There's no truncation attack, there's no impersonation attack, nothing happened. ماشي كده? So this is this part. And then it sends certificate request. يعني certificate request يعني ايه؟ عملت اللي عليها اهو. You need to do the same بقى. You need to authenticate yourself. So the server would send a certificate request, which means that the client needs to perform his part of the authentication. ماشي? And then the server will say, server, hello, done. I'm not going to report any more messages. So now the ball is at your court. You need to do your part. The server will do the same. Based on this certificate request, it would send a certificate to authenticate itself. This, by the way, may be a user ID and password, depending on the request from the server or depending on the authentication that they agree on. And then the client key exchange, the client would do the same to make sure, again, that all the messages before this have been actually, in fact, sent by the client and no one else. So again, the client would report the public parameters for Diffie-Hellman and the signature, which is a hash value, again, encrypted by the private key of the client. ماشي? And then the client would send a certificate verify, which means that I verified your authentication, and now we are here. We have actually not a master key. We have what we call pre-master key. Here we have pre-master key. So this pre-master key, here by the client and the server, they would do multiple steps. Here at this part, at step 1, we have the pre-master key. Then we convert the pre-master key to a master key. So these are two steps. And so from the master key, we create the connection state for all the upcoming connections. If we use multiple connections in parallel, then we have to create multiple connection states for each single connection. ماشي? If it's sequential, then we create one connection state, depending on the interaction between the client and the server. Then the client would send the change cipher spec to use that cipher spec for all the upcoming connections, and it sends finish. This finish, by the way, برضو also has some signature. And this signature is the accumulation of all the messages sent by the client before that. يعني as a type of verification. That's why يعني TLS is very, very hard to break. فعلا يعني very, very hard to break. And that's why it's been widely used in not just web, not just يعني web services, but in different types of services, and not just for client server, by the way. It's used for peer-to-peer communication for different services. ماشي? So this is the key exchange and the change. By the way, here it's random sequence. I forgot to say that. Random sequence is exchanged as part of the client hello and the server hello. So in the client hello, we exchange the random sequence as well as all the capabilities of the client and the server. ماشي? Why do we need to exchange the random sequence here? Respect. So the cryptographic computation, so there are two further items out of interest, the creation of the pre-master key. So similar to what we have done before in other security services, why we have two steps, we have pre-master key and a master key. Because again, depending on the authentication method, we may end up with different size of keys. Okay, so what happens is that, as we said, as part of the connection state, the server and the client, they exchange what we call sequence pattern or sequence, random sequence, اللي هو to come at this step and create the master key, which is a pseudo-random function of the pre-master key and the random sequence. بالإضافة لإيه؟ In addition to other parameters. Sometimes these port numbers, timestamps, things like that. Okay? So the master key is a function of the pre-master key and the random sequence. And that's why they exchange it. Yeah, nonce يعني. Okay? Then we use بقى إيه? That master key for the generation of the cryptographic parameters for the cipher spec and for all the upcoming connection states. اللي هي بقى including the server write key, client write key, IV, everything else. Okay? And these can be created as using some key expansion techniques from the master key, similar to what we have done before. The heartbeat protocol. The heartbeat protocol is a periodic signal generated by the hardware or software to indicate this is in general the concept بتاع heartbeat. A heartbeat protocol is typically used to monitor the availability of the protocol entity, and it runs on top of TLS record protocol. It consists of two messages: heartbeat request and heartbeat response. So heartbeat request, heartbeat response, and that's usually exchanged between the client and the server, even if the user is not interacting on the session. Even if the session is idle, there's no traffic, we need to keep sending these messages with a specific frequency and for a certain duration of time to maintain this session valid through all the intermediate firewalls and devices. So it assures that the client recipient is still alive, even though there may be no activity on the session. And it generates activity across connections during idle periods, which avoids premature closure by firewalls. ماشي? So these are the protocols. طبعا so these are the types of attacks. Again, there's nothing new here. So there are certain attack categories that happens for web services and particularly for SSL and TLS. There are some attacks on the handshake protocol, and that sometimes is performed through some truncation attack. Truncation attack is some type of attack that مثلا a message is being sent between the client and server, so the attacker comes in the middle and tries to block this message from reaching out to the server. Okay, طبعا this is followed by a message, a manipulated message from the attacker side to try to impersonate into the communication. So I truncate and then I impersonate to try to give some false information to the server to facilitate the fact that I can break this communication. So that type of attack is very common, particularly for web services and for end-to-end client-server communication. So again, the attacks here are not attacks particularly on the mechanism, because as we said before, the mechanisms themselves are secure, and there's no flaws in the mechanism itself. The flaws are always in the protocol level messages, and that's what commonly attackers utilize as attack surface to try to break into the communication. Attacks on the record and the application, so that might actually include some traffic analysis, some guessing of the key, but طبعا again one of the secure features of TLS, which is again inherited from the fact that HTTP is using short-lived TCP connections. So these connections are short-lived connections, which means that traffic analysis will not probably be successful here, because the connections are very short, and by the time you guess, the connection is gone. Unlike SSH, we'll talk about SSH later. SSH uses different concept. We'll talk about that. Attacks, of course, on the key exchange, as we said, and other types of attacks, which includes all the standard attacks that we talked about before. Type. So HTTP over SSL here, طبعا احنا, as we said before, SSL is considered to be a light version of TLS. So TLS came to try to provide more security robustness to the client-server communication, and try to deprecate SSL, but again, it did not work very well, and that's why they tried to upgrade to TLS version 1.1 and 1.2 and 1.3 now to try to provide some backward compatibility. So the HTTPS capability is built into all modern web browsers طبعا, again, or طبعا حتى in the operating system itself. So any service other than web can also use TLS through the integration of TLS in the operating system. If HTTPS is specified, then this is the server port طبعا, port 443 is to be used. طبعا many browsers now, when you say HTTPS, they invoke TLS, not SSL. Now, yeah, ماشي. طبعا there is no fundamental change in using HTTPS over either SSL or TLS. For the web browser, the change from TLS or SSL is actually seamless. But of course, TLS is more powerful when it comes to security, robustness, and efficiency of the handshake protocol as well. The handshake is performed much faster for the case of TLS, especially TLS version 1.3. They try to provide, because the handshake process, as you can see, is kind of expensive, exchanging messages back and forth. So مثلا in TLS version 1.2, this handshake protocol may actually take مثلا maybe half a second or 1 second, which is kind of significant. In 1.3, they try to reduce this process significantly. So when HTTPS is used, the following elements of the communication are encrypted. So everything basically, with the only exception of the TCP header, is encrypted. So anything in the application level payload is encrypted. So anything including URL, the URL itself, because the URL is part of HTTP header. This is the encrypted. Content of the document is encrypted. Content of the browser forms, cookies, everything is encrypted. Even the HTTP header itself is encrypted. ماشي. طيب, the connection association for HTTPS, طبعا the agent acting as the HTTP client is the one that acts as a TLS client, which is natural. So the TLS client is the HTTP client. So the client initiates a connection to the server on the appropriate port and then sends the TLS client hello, which is part of the handshake protocol, which instantiates the the handshake process and the user authentication and key exchange. When the TLS handshake has finished, the client may then initiate the first HTTP request to start to exchange some information now in a secure way using the TLS connection state. And there are 3 levels of awareness or 3 levels of connection. طبعا هنا احنا, as we said, HTTP works on top of TCP. So now TLS comes in the middle. So HTTP works on top of TLS, and TLS secures the communication of the TCP connection. So at the HTTP level, an HTTP client requests a connection to the HTTP server by sending connection requests. Typically, the next lowest layer is TCP. So the first thing that happens actually before the handshake is to establish the TCP connection. The TCP connection gets established, and then we start to exchange the handshake protocol to provide security on top of TCP. So that's usually what happens. At the level of TLS, a session is established, and then the session instantiates TLS connections, multiple connections, one-to-many. A TLS request is established. To establish a connection begins with the establishment of a TCP connection. So first, we establish the TCP connection, and then we perform the handshake. From the handshake, we create the TLS connection, which works on top of on top of TCP to create the tunneling service. Nothing is new here yet. Type connection closure. That's an interesting phenomenon. In the standard, there was some issue, and again, I'm not sure if it was fixed as part of TLS version 1.3. So HTTP client or server can indicate the closure of a connection by including the line connection closure. So in network 1, we talked about the fact that if we have a client and we have a server, TCP provides some kind of bidirectional communication, right? So that's TCP. TCP provides connection-oriented and bidirectional communication. So when we create that connection, we do the TCP connection establishment, right? طبعا هنا يعني the record protocol provides some kind of tunneling on top of this. Naturally, right? What is the problem here, Brad? The problem is that when we finish the communication, usually for TCP, if you remember, we send like a FIN message. If you remember, as part of the disconnection, we send a FIN message, right? The client would send a FIN message to the server, right? So when we send a FIN message, the connection establishment is done synchronously, but the connection closure is done asynchronously by TCP. And what that means is, when the client sends the FIN message, the client reports to the server that I don't have any more data for you, which means that the client may in fact, this is the socket. The client may in fact terminate the socket, flushes all the buffer for the socket completely, right? And corresponding to that, we have a connection state. And the client may in fact also terminate that security connection state or TLS connection state. Because already I'm finishing. But by definition, for TCP, if you remember, if you go back to connection to network 1, as we said, the FIN message is sent separately by the client and the server. So when the client sends a FIN message, the server may in fact continue sending some information before sending the FIN message. That's when the problem happens. Then in the standard, at least up to TLS 1.2, they did not talk about trying to control the synchronization of connection closure between the client and the server. Okay? So from a TCP perspective, that's okay because there's no security issue. There's no security خالص. We don't care about security. The client sends the FIN message, it terminates the socket, the server may continue sending some information, and after some time it sends a FIN message. So here, the socket here gets terminated, right? So it used to work. The problem with this TLS integration here, this will not work from a security perspective. Why? Because if you actually send a FIN message, the client may send a FIN message, and based on that, it terminates the socket, and it may actually terminate the connection state for the security. What might happen here is that the attacker might come in the middle and perform what we call truncation attack. It breaks this message from reaching to the server. Okay? If the attacker blocks this message from going into the server, now for the server, the client is still there. صح? And the server may still continue communication. But here, everything here is terminated. So the server may in fact talk to the attacker instead. So the attacker may block this message, and the server may continue sending information, and the attacker may actually impersonate and break into the communication and try to communicate with the server. The problem with this is that the connection closure is not synchronized, or in other words, it's not reliable. بمعنى إن it's done by the client independently from the server, and by the server independent from the client. So when we add the security perspective here, it would be nice to the fact that the server may send the FIN message, and then the client would send the FIN message, and then the server acknowledges that and send back a confirmation that it has received that FIN message, right? And then and only then, the security context at both sides will be concurrently terminated. Okay? So from a security perspective, that's important. From TCP perspective, it doesn't matter, right? Because we don't care about security. So again, in the standard, they did not actually specify one method or the other. They did not dictate the fact that this has to be done synchronously and reliably or asynchronously. Okay? So that's why some بيقول لك هنا a TLS implementation may, after sending a closure alert, close the connection prematurely without waiting for a confirmation from the server. Because that's how TCP is designed. So we'll do the security at TLS level the same way, right? But that's not correct, because this will facilitate the truncation attack. And these are the loopholes that the attackers usually work to try to use as attack surface to break into the communication. So that's why in some TLS implementation, and they still comply with the standard, they have this issue, okay? And I'm not sure if version 1.3 they have mentioned that explicitly in the standard or not. I'm not sure. I have to verify. But this is one of the issues that existed as part of the connection closure. So connection closure is done asynchronously, following the same approach of TCP, providing connection or disconnection, again asynchronously. Okay. But from a security perspective, it's very important to do that synchronously and reliably, which means that we need to verify the bidirectional communication for the connection closure before we dismantle or terminate the security context. This is very, very important.
I just don't get
Message.
Message gets received directly by the server, and then like if the server still has something to send to the client, and what happens? Like, does it send it over in secure connection or what?
It would still send it through the security session, right? Because it depends on the implementation of TLS at the client side. Just the fact that I sent a FIN message, it doesn't mean that I dismantle or terminate the security context. I cannot terminate the security context until I get a confirmation from the server that indeed the server has received. And of course, this is done through a secure channel, so no one can break. If we have this reliably, no one can break into the communication, right? So I will not terminate the security context before I receive a confirmation from the server that indeed the server has received the FIN message and it has indeed finished all the communication with the client. Then and only then, both of them will terminate the security context at the same time, synchronously, not asynchronously. هي دي مشكلة. Okay? يعني هو TCP لما جينا شرحنا for connection establishment, we always say that the server would send its own connection start, and at the same time it acknowledges the fact that the client has sent a connection establishment. So we merged both into one message. But for the connection, for the disconnection, we cannot do that. Why? Because the server may send the acknowledgement, but may still continue communication and then later on disconnect. So for TCP, that might work. For security, that should not work because of the fact that there is some attacker in the middle who might actually utilize that to provide some truncation attacks and so on and so forth. So the connection closure needs to be done synchronously. ماشي كده؟ طيب, so an unannounced TCP closure could be evidence of some sort of attack, so HTTP client should issue some sort of security warning when this occurs. So we can in fact use بقى alert protocol in that particular case to report some warnings or some fatal mistakes. But more importantly, if the TLS implementation itself provide that secure connection closure, or synchronization for the connection closure, then we will not have an issue at all. Okay? طيب. خلاص, we'll stop here. So this is SSH. So for SSH, it's another type of transport layer security that uses slightly different concept. But again, it started again as the main objective is for SSH to be used for remote login, to work on top of Telnet, if you know Telnet. For remote login and for again, it's a type of client-server communication, but it's a different type of service. But again, SSH proliferated to be used in other services as well, similar to TLS. But there are certain differences which we need to talk about. But the main approach is the same. Okay, so we'll talk about this next time.